Thank you.
Okay, so roots with even indices cannot output negative values. Okay, so that's a good way to sum that up. And roots with odd indices can output negative values. All right, let's do some practice using all of these properties. Examples using root, I'll just say, root properties. I'll just call this number 1. Okay, so let's say we want to simplify the cube root of x to the 4th. Cube root of x to the 4th. Now, I'm coming into a thing where you may have learned this a different way, and that's totally fine. Like if you learn this some other way, but I'm going to show you the way that emphasizes the use of these properties that we just wrote down. In particular, the first 2 properties. The first 2 properties are probably the things we're going to use the most. 3, we're not going to use that much, and 4 or 5 are important, but they're kind of like an afterthought for each problem. So how can I simplify? So that's the instructions. So for each, we're simplifying each. How can I simplify this? Well, what I want to do is try to get it to a place where I have a cube root of x cubed, because that can be simplified to just an x. So what I can do, so the idea here is to say, well, this is the same as x cubed times x to the 1st. Okay. I can split any x to the 4th up this way because our exponent rules tell us, 3 plus 1 would be 4. So this is a legitimate way to split up x to the 4th. And now by that property 1 that says if you have the product of 2 things under a radical, you can split it. I can split this 3rd root, or this cube root, remembering to put the cube root, the index of 3 on both of these. I'll just say x. I'll drop that 1. That 1 is not necessary. I put it here to emphasize where it was coming from, but now I'll drop it. And then, so what is, according to rule 4, or just your intuition, what is the cube root of x cubed going to give us? Braden, what do you think x cubed under a cube root? What will this part turn into? How about Kimberly?
It'll just be x.
Right. This part will be x. And then the rest of the problem, this part will just carry over. So what have we done? We've said the cube root of x to the 4th is the same as x on the cube root of x, like that. So whenever they're being multiplied, we can suppress that little notation saying they're being multiplied and just stick them together just like this. Okay, so let's try another one. Okay. I'm going to stick with what the book's doing, and then we'll probably deviate after these examples just to give you more to think about. The 4th root of 81, x to the 4th, y to the 8th. Oh, that's fine. That's close enough to what they have. Okay, so first thing we can do is split this radical around these 4 products here. And then we can deal with, or these 3 rather, these 3 terms, and we can deal with each of them individually. So this is a super powerful rule. You can already tell we're using this rule to pull apart products of radicals, already using it a whole lot. I don't really like how they wrote it out in the book. That's okay. All right, so the first thing to look at is, do we know what the fourth root of 81 is? That's kind of a separate issue. That's kind of like just knowing, you know, being comfortable with products of numbers. So we want some number times itself 4 times that equals 81, and there may not be such a number. So what can we do there? What I'd like to do is isolate this as a separate example in the next example about what you can do with this. But for now, what I'm going to do is I'm going to go ahead and tell you that there is such a number that does this for us for the number 81, and it's the number 3. So that means the fourth root of 81 is just 3, because it's asking what number times itself 4 times give 81, but I've answered that here. So the first part is just 3. So we're getting just 3 there. So this part literally just turns into a whole 3. Now, the next piece is the fourth root of x to the fourth. Well, I know those are going to cancel, that fourth root and that power of 4 there, but I do need absolute values around it according to that rule number or property number 5. Okay, and this is to make sure that I'm not outputting a negative from my fourth root. Now, what about the second one? So now we're pushing the rule a bit further. So Aviana, what do you think would come out of the fourth root of y to the 8th?
Could you divide the 4 and 8?
Yes, that's actually getting ahead. Well, what does your intuition tell you? Like, if I wrote a y, what would the exponent be?
Would it be 2?
That's right. That's right. So later we're going to learn, actually, when I say later, I mean like in a few minutes, we're going to learn a rule that justifies what you said about dividing the exponents. But for now, hopefully your intuition is telling you if it takes 4 y's to get out, but I have 8, well, that's 2 groups of 4, so it's 2. Good. Now, do I need absolute values around this? No, I don't, because this exponent here is even, which absorbs any negatives. So here I need a negative because what if x is like, I don't know, -5, right? So I need absolute values to make sure I'm not outputting a negative from my fourth root. Here, if y is -5, it doesn't matter because that little even exponent is going to absorb the negative. So even exponents outputted from a root like this, they're okay. They don't need absolute values. So I can make a note of that. Don't need absolute values. I'll just say ABS values, since exponent is even. Don't need absolute values since exponent is even. And by the way, if I cleaned this answer up without the little dots for multiplication, the more natural way of writing it would be just like this, without the dots. The dots aren't wrong, it's just they're not necessary. All right, so let's look at an example. What we're going to do is we're going to look at an example where we break apart a number instead of variables. And then we will get to that rule that Aviana was alluding to. Okay. Okay, so number 3. Number 3, let's simplify. Let's start, we'll probably actually do 2 of these. Let's do square root. Oh, I don't need a huge square root. 1 second. Okay, if your screen froze, it's just the Wi-Fi wherever you are. But I'm recording the meeting, so if you miss part of the meeting, you can always view it afterwards on Canvas. just one of the things we have to deal with being remote like this. Okay, so let's simplify square root of, let me think, let's see, let's do something not too crazy. Let's just do 52. Square root of 52. All right, so the naive thing to do would be to plug it into the calculator, but then it would give you some terrible decimal number. That's not what we want here. So the point is, this is not a perfect square. So we need some procedure to be able to simplify this. So I'm going to get straight into it. The first thing we do is look for a perfect square factor in 52. And remember, perfect squares are like 4, 9, 16, 25, 36, 49, etc. Perfect square numbers. We need one that's a factor. Why am I looking for a factor? Well, a factor lets me take a number and pull it apart as a product of two numbers. And if I can get this split into a product, then I can split the radical, right? Because that's what that tells us we can do. That rule number one, or property number one. So can we think of a pair of numbers that multiply to give 52, where one of them is a perfect square factor? So after you think for a while, you can take 52, start dividing it by perfect square numbers. Eventually you'll figure out that 52 is the same as 4 times 13. Okay, that's my perfect square factor. Okay. Now I can split the radical into 2 square root of 2, or sorry, not 2. I'm thinking ahead. Square root of 4 times square root of 13. But square root of 4, the reason I picked square root of 4 is because it simplifies to just a 2. So I'm getting 2 times the square root of 13. Nothing else can be done with 13, right? It surely does not have any perfect square factors. In fact, it's prime, right? It has no factors other than itself and 1. And if I really wanted to just clean this up, I could write it like this without the multiplication dot. All right. Let's simplify a cube root. So this time you're going to look for not a perfect square factor, a perfect cube factor. So remember those lists of squares and cubes I gave at the very beginning of our first lecture. Those are going to come in handy now. So does anyone want to venture a guess as to what a perfect cube factor of 54 might be? So remember, perfect cubes are 8, 27, 64, 125, etc. So anyone want to guess which one of those would be a factor of 54?
27 would.
Right, so I could write this as 27 times 2, right? And how do you find out what the other factor? Just divide it, right? Just take 54, plug it into your calculator, and you'll get 2. And now I can split it. Split it, and I have to know what cube root of 27 is, right? I have to know that, and it is 3. 3 times 3 times 3 is 27, so that means what number times itself 3 times gives 27, and it is a3. And then I'll just say with the cube root of 2 attached, which cannot be simplified any further. So that's how you can deal with these numbers. Okay, good. Now let me go. I'm going to go look through the homework and see if I can find one of the harder ones that deals with this. And I'll do it with you guys. It's just taking forever. And then we'll talk about that rational exponent rule. In fact, it's loading up. While it's loading, I'm going to go ahead and write the next rule down. Okay. I'll leave some space. So I'm going to leave some space in the notes for another problem, and then so here comes the big rule about rational exponents, which is going to be the justification for all the rules that you know that I told you, the justification for that thing that Aviana mentioned. If you have a root, an nth root of some value a raised to some number m, that's the same as having a raised to an exponent of m over n. So let's make a note. The index, which the index is that little number there, becomes the denominator. So quick examples here. Quick examples. The cube root of 2 would be 2 to what power? The denominator is the index. And let's see. Is Dorcas here? Yeah, okay, so Dorcas, what would the numerator of the little fractional exponent be? Okay, how about Devon? Do you know what the numerator of this exponent would be?
Would it be 1?
That's right. So when it's not explicitly written, we understand that value to be a 1. So that's good. Yes. So the cube root of 2 is the same as 2 to the 1/3 power. Let's see, what were we looking at earlier? It was a 4th root of y to the 8th. This is Aviana. This is what you were getting at. Yes, this is the same as y raised to the 8/4, which, by the way, lets us say 2, right? 8/4. So if you've got good fraction simplification knowledge, you know how 8/4 works, then you can quickly get from something like this to this. Now, if you still look at this and say, well, it's better for me to understand 2 groups of 4, you know, in 8, so it's y to the 2nd, that's fine too. It's the same thinking. It's just, you know, this is just more so hammering home this rule that any radical root thing can be written with rational exponents, and back and forth, vice versa. So let me, before we keep digging into rational exponents, let me find some let's see, what can I work with here? Okay, I got a couple more quick examples, just simplifying radicals. Let's look at, what was it? 5. Okay, number 5. The cube root of 3 over the cube root of 192. How can we deal with this? Well, property number 2 tells us that if you have 2 separate cube roots, you can put them together under one radical. Why would that be useful here? Well, because if I put them under the same radical, like this, then I can try and simplify the speaking of simplifying fractions, I can try and simplify this inside, which will make my problem much easier. So does anyone know what 3/192 simplifies into, or how you could figure it out? We can do 192 divided by 3, which will tell us what ends up in the bottom. And we see that the result is 64. So that means I would have a 64 in the bottom and a 1 up top. 3 goes into 192 64 times. Okay, now I can split it back apart, cube root of 1 into cube root of 64. But cube root of 1 is just 1. Any nth root of 1 is just going to be 1. And then what's the cube root of 64? Well, it's 4. So this is equal to that. Okay. Let's do another quick one. The cube root of, see, this is a tricky one, 128 minus cube root of 54. You cannot put these together. Your instinct may be to push these together under one radical and just do 128 minus 54 and then deal with the cube root of the result. Can't do that. The only two operations you can do that with are division and multiplication. So all we can do here is try to simplify each of these, and then maybe once they're simplified, we can sort something out between these two. So we've already dealt with the cube root of 54. We found that was 3. So I'll leave a space and then minus and then 3 on the cube root of 2. We simplified that into that. That was problem 4 when we did that. What about the cube root of 128? So what I'll do is I'll type 128 into my calculator and I'll try and think of a perfect cube that goes into 128. So I might try 27 and it doesn't work. I might try 64 and it does work. So it turns out cube root of 128 is the same as 64 times 2 under a cube root. So I'll do it over here just in the, to save the room, is the same as the cube root of 64 times 2. The cube root of 64 is 4. So I'm going to skip a step here, and can I just say, is everyone comfortable with me just doing that? 4 on the cube root of 2. So that 64 became a 4. Okay. So now I have 4 on the cube root of 2. That was the cube root of 128. And then what happens here? Does anyone have any idea what I can do now since they look the same in their roots?
Do they cancel out?
Not so much cancel out, but think of it this way. Think about replacing this cube root with an x. 4x minus 3x is 1x, right? So 4 cube root of 2 minus 3 cube root of 2 is just going to be 1 cube root of 2, which we would just write as cube root of 2. So let me, because this is kind of like one of those things that's so much notation is suppressed here that might be a bit confusing. Let me go a little bit further into that, and then we'll get back to this rational exponent stuff. All right, so 4 cube root of 2 minus 3 cube root of 2. Now, does everyone agree that I could factor out a common factor of cube root of 2 out of both of these? In other words, can't I do this? Just factoring it. Remember your distribution property, but in reverse, right? Factoring out the greatest common factor. So this is a legitimate thing. But what's 4 minus 3? Is 1, right? So cube root of 2 times 1, but that's just cube root of 2. So that's another way to see what's happening here. So you can subtract or add once the radicals completely match each other. And as long as there's no other, if there's variables involved, they have to match too. So that can get a little crazy, but when it's just numbers, if the roots exactly match each other, then you pretty much just add or subtract their whatever this term is, the coefficient there. Well, I guess you wouldn't call it a coefficient, but whatever the whole number term is. In other words, in this case, 4 minus 3. And when it's just 1, then you don't have to write the 1, right? Because it's understood to be there. So, all right. Rational exponents. Let's get back to that. One second. All right, here we go. Write each using rational exponents. A. Let's say we have the cube root of x squared. Cube root of x squared. Well, that'll be x, and now I'm writing it as a rational exponent, so it's going to be a fractional exponent up here. The denominator should be that index, and the numerator will be the number inside there. So there we go, x to the 2/3. All right, how about b? Let's say 1 over square root of x. What does this one definitely have to involve since x now is in the bottom? Remember how we dealt with that with exponents last time? If anyone has an idea, you can speak up. So how can we deal with x being in the bottom? What needs to be involved in our exponent? It'll be negative. Negative is going to say this x is actually in the bottom. And then with a square root, how do we write the square root in rational exponent form? Well, everything is suppressed, like all the notation is suppressed here, but we understand that the index is a 2 on a square root, so that means my denominator is a 2. It's a 2. And then the exponent inside, we saw earlier, like with this example, when it's not written, it's understood to be a 1. So when you have 1 over square root of x, that's the same as x raised to the negative 1/2. Let's go backwards now. Let's write each using radicals. Okay, so we'll go backwards. How about 5 raised to the 9/8. Okay, I look at the denominator. I know that's going to be my index, so I'm going to draw my little root thing. My index, which is the number that goes here, that's the 8. The 5 is the number, the big number inside, and then there's going to be a 9 on it. Now, could I simplify this? Yes, I could do some work with this to simplify this, but just writing it using radicals, this is all I need to do. What about 1 over square root of x to the 8th? Oh, wait, no, sorry. I gave you the, dang it, sorry. I'm supposed to give you the rational exponent. So let me say x raised to the, I'm going to change it slightly. Let's say negative 7/3. X raised to the negative 7/3. And I'm going to write the solution down here since I'm a little bit out of room. So it's negative. That means it's definitely going to be in the denominator. And I'll just write a 1 up top as a placeholder. It's under a cube root because that denominator of the little fraction up here is a 3. So it's under a cube root. And I know there's an x inside. And the exponent on the x should be a 7. So notice there's no negative sign happening here because I used the negative up by putting the x in the whole thing in the denominator right here. Okay, so any questions about that? Well, if you think of some questions while I look at these problems in the homework and I'm just going to decide if there's anything I need to emphasize. Here's one I'd like to do. Let's do I'm going to change it slightly. The 5th root of y to the 6th times the 4th root of y cubed. So I'm changing it slightly, but how can we deal with this? And we're going to express the answer using rational exponents. So we're going to express the answer using rational exponents. Well, I can write this first one as y to the 6 over 5. And the second one as y to the 3 over 4. And let's see, who am I going to call on? Maya, what is the rule for these exponents when you have a product of two numbers? They have the same base. What do we do with the exponents? Does anyone remember what we do with the exponents when we have a product of two things that have the same base?
You can just use it as they're the same, so you can do 6/5 and 3/4.
And what do we do with 6/5? What operation do we use to connect those two? We use addition.
Yeah.
So that's how we connect them. So we say 6/5 plus 3/4. Okay, and now we have to, this is where we have to recall our fraction addition rules. Common denominator, you know, so this would be the same as common denominator of 20. So that would be 24 plus 15. And that would give me 39 over 20. There we go. So kind of a long walk to get there, but the idea is if you've got the product of two weird radicals, you can write them in rational exponent form. Then you can use exponent rules. So that's kind of the point. The point of writing of this whole rule, writing radicals as exponents, is that now it's a justification for using all the exponent rules we have on radicals, like this, for instance. All right, so let's talk about rationalizing denominators, which is a kind of a changing gears a little bit, but okay. Okay, real quick, to rationalize a denominator just means to get rid of radicals in the denominator of a fraction. Because radicals are inherently irrational numbers. So to rationalize something means to get rid of the irrational numbers, which in this case are radicals in a denominator of a fraction. So as an example, let's just take 1 over the square root of 2. What can we do to get rid of the radical in the bottom? Well, the only thing we're allowed to do with an expression is either add 0 to it, which is not going to be useful here, or multiply by 1, which you might also say is not useful. But what if I multiply by 1 in the form of square root of 2 over square root of 2? Why would I do that? Why would I do that? Well, recall your fraction multiplication rules, just multiplying straight across. In the top, I end up with a square root of 2, because 1 times square root of 2 is just square root of 2. In the bottom, I have square root of 2 times square root of 2. Square root of 2 times square root of 2. But that's the same, remember, as square root of 4, because since it's a product and they're the same type of root, I can push them together, and 2 times 2 is 4. So I've got a square root of 4 here. But what is the square root of 4? It's 2. And now I've successfully gotten rid of the radical in the denominator of this fraction. I have rationalized the denominator. So this is done. Okay, that's how rationalizing the denominator goes, at least for square roots. So let's move to, I guess, problem 10. Let's say we have 3 over square root of 5. So what should I multiply by? Anyone can speak up if you have an idea.
The square root of 5.
That's right, in the top and bottom, right? Yeah, top and bottom. Because technically, in the red, what I'm multiplying by is technically just 1, the number 1. It's just a special form of 1 where it's, you know, a root over itself. And that basically here has the effect of, in the top, just squishing these two numbers together. That's fine. And then square root of 5 times square root of 5 is going to be the same as square root of 25, which of course is just 5. So that's the point of doing it this way, is that the radical is always going to cancel in the bottom. Now the top, I just carry along just like that. Oh, I should have been writing in black to finish it, but whatever. That's it. That's done right there. Okay. What if I have a cube root? Wait, let me look. Let's call this A, and then I call this one B. Before we get to cube root, let's look at this. Let's look at x over 6y, all under a big square root. What can I do with this? Well, I can say that this is the same as square root of x over square root of 6y. So splitting it apart first. That's the first step there. So these two first examples I did, they were already split, or really the top wasn't under the radical at all. But now if I have the entire thing under a radical, I need to go ahead and split it. And now I'm just going to mimic kind of what I was doing in the other steps and multiply by square root of 6y, whatever's under here, square root of 6y. Okay, now in the top, they all just get stuffed up under the radical, 6xy, because they're all under a square root, so I just stuff them all together there. Now in the bottom, the same thing happens, they all get stuffed together, but 6 times 6 gives me 36, and y times y is y squared. So then in the top here, nothing really happens, but in the bottom, the square root of 36 is 6, and the square root of y squared is just y. There we go. So that's how we can do it when you have numbers and variables all together there. And so the top is still irrational, but that's okay because this is called rationalizing denominators, not rationalizing numerators. All right, now the next thing is to look at rationalizing denominators that are not square roots, but I'm kind of out of time. Dang. We are. Give me 1 second. I want to look at section 6 and see how much. Okay, so here's what I want to say. We're moving pretty slow, which is fine. I want to try to not to have to adjust what's going to be on the exam too much. So what I'm going to say is for section 6. Let me show you what's going to be on section 6. Section 6 is kind of like your basic factoring techniques. So, all right. Come on, let me see my tabs. There we go. What I'd like for you to do is go look at section 6 in the homework and the text if you'd like, and see if you can do them on your own, because you've seen all this stuff before. If you took MS 100 here, you've seen like these special factoring formulas like difference of squares. You should know how to factor out the greatest common factor, things like that. So what I'd like to do is see if you can see how far you feel like you can get in section 6 on your own, and then we will, instead of me going through the entire thing on Friday or whatever day, I don't even know what day. Yeah, Friday. I would like to just hit the things that you feel like you don't remember. So go look through the homework for section 6 in addition to section 4, 0.4 and 0.6, and see what you can do in that factoring section. Make note of the problems you don't know how to solve, and we'll go over them in class on Friday, and then we'll move into chapter 1. All right, that's it. I'm going to stop recording. You can stick around if you have questions about anything, but if not, you guys are good to go.